Pavlos and Mabel, thank you very much for this kind invitation and giving me opportunity to show the last results we make in the collaboration, also with Skoltech. Doesn't work. Oh, it works. Doesn't work. Today, as Pavlos already mentioned in the introduction, I would like to discuss the optical gain and lasing from inseparable states. And I will start the presentation about the concept of liquid crystal optical microcavities. Then I will show the Rashba-Dresselhaus spin orbit coupling for photons. I will discuss the persistent spin helix and inseparable states, and at the end I will show the lasing. This work was done in the collaboration with many groups. We are the group at the Faculty of Physics, University of Warsaw, but the samples are prepared at the Military University of Technology with a group of Viktor Piecek and Przemek Kula. We have a very fruitful collaboration with Skoltech and University of Southampton with Pavlos Lagoudakis and Helgi Sigurdsson, and with Polish Academy of Sciences, Institute of Physics from the group of Michał Matuszewski. We also received some funding from European Union and from National Science Center. Before I start, and before I forget at the end of this talk, I would like to show the credits for my group, which we lead with Barbara Piętka. There are a couple of people, and as Pavlos said, we established it about a decade ago. And since then, we managed to enter to this research of polariton physics and strong coupling and the weak coupling with some papers, and which some of them I will present today. Okay, so let me start with the optical cavity. Actually, we are dealing with the basically fabric resonator. Yes, so this is the optical cavity made of two parallel surfaces, and the fabric and the Perot they explain the color of soap bubbles, for instance, as the multiple reflection of the system inside this tiny cavity of the with the length of this cavity was of the order of the optical path, and the optical path was defined by the thickness and also by the refractive index. And in our research, we decided to tune the optical modes not by changing the thickness as it was typically done in this field of microcavities, but by tuning the refractive index. And in order to do that, together with the Military University of Technology, we developed this idea of birefringent liquid crystal microcavity. So there is the active medium inside. This is the liquid crystal, nematic liquid crystal, uniaxial, and it is closed between two distributed Bragg reflectors, and there are two ITO transparent electrodes to apply electric field. There is also another special so-called raving layer, the special polymer, and this polymer aligns making an order of the molecules. So when we apply the electric field, the molecules rotate, and the optical mode, the optical path for the light inside the cavity changes. So we can tune the mode. The first cavity was quite bulky because we were afraid that the capillary tension just bent the glass, but now the cavity is maybe more compact. This is the movie how we tune the cavity using this nematic liquid crystal, and we use the possibility for the liquid crystal that they change the reflective index at least in one direction, or maybe only in one direction. So there are two optical modes, and one optical mode is not affected by the change of refractive index. This is we call it vertical mode, and the horizontal mode indeed sees this rotation of molecules. So if we look at the experimental data and even the calculations which are performed with Berman matrix method, we can observe that the modes split, but this is due to the change of the energy of the horizontal mode. So I will start the movie now, and we see that there is one mode which which rests at the same energy, and the other which approach the other one, and then some modes just crossing, some they interact, and this is actually the main subject of our research, to understand and to use this interaction between the modes. As you have seen, when we rotate the molecules, the vertical modes stays at the same energy. So this is the cross section of the multimode cavity with k equals 0 and the energy position of the horizontal and vertical modes. And when we start the rotation of molecules, and if we have the alignment of the molecules that they start with the perpendicular orientation regarding the surface, then we have the two modes with the same parity, horizontal and vertical. But then we apply electric field, and one of the mode is decrease this energy, and the second mode at different parity and the different number of nodes or antinodes approach, and then at a certain molecular orientation, this is in resonance with the cavity. So we called it N+1 and regime. This is a horizontal vertical basis. And then there is another regime which we can investigate, and the N+2, etc., depending on the thickness of the cavity. In order to describe the light propagation in the system, we of course can characterize the light by the energy and the momentum, the angular, the angle of the light which is coming out from the cavity. But also, as you see, the very important part is also the polarization. So we describe this polarization in terms of the Stokes parameters, which can also be transferred to the Pauli matrices. And the Pauli matrices gives the how to say, there is some correspondence between the polarization of light and the spin of electrons. So instead of Bloch sphere for electrons, we are using one Carré sphere. Maybe the meaning of spin up, spin down, sigma plus, sigma minus can be plotted differently. But nevertheless, this is very useful mathematical representation of the polarization of light. And both direction of light, so the momentum of light and the polarization of light, means the spin of light, leads to the many effects of so-called spin orbit interaction of light. Then we can try to describe the spin orbit interaction in terms of well, first of all, we can solve the Maxwell equations. Yes, so this is what we did in our science paper. But then you can represent this Maxwell equation in the form of Hamiltonians, and actually very basic interpretation with symmetry groups, with symmetry operators in our cavity, allow us to predict what kind of spin orbit interaction are symmetry invariant. So regarding our cavity, it's mostly C2H symmetry for most of the situations. and then one can apply the symmetry transformation to vertical and horizontal mode of different parities and the propagation of light in kx and y direction, so in plane momentum. And then one can, for instance, decide what is the irreducible representation, for instance, for this mode in case of, for instance, in inversion. So inversion doesn't change this mode, but the mode of this kind does change, etc. Of course, in the situation when is the most interesting for us, we are dealing with two modes, horizontal and vertical. So we can exactly the same procedure apply for the pair of modes together with Pauli matrices and together with all the symmetry operators, and then we can deduce and what are the symmetry invariants allowed in our system. And this discussion you can find in our Optica paper, which came this year, and Witold Badaszewski proposed this elegant way of presenting the spin-orbit interaction in our system when we restrict our the solution to two modes which are close to each other, like KP approximation in solid state, so we can, together with time reversal symmetry, which is that changes the k to minus k, and the time is just the complex conjugate. You can predict all possible symmetry invariants regarding the product of Pauli matrices, means the spin, the polarization of light, and the moment. By applying the Maxwell equation, we can calculate those parameters, which previously I just marked by alpha 1, alpha 2, alpha 3, etc. So we can write this in a way that it resembles the Hamiltonian for solid state physics. And the parameters, they are just the parameters of the cavity. So you have extraordinary and ordinary refractive indices and the angle of the rotation of molecules. And you can calculate it just for any regimes regarding the parity of the system. It's interesting that we can deal also with so-called synthetic magnetic fields or artificial cages. I will refer especially for the case of this Rashba-Dresselhaus term that we can interpret some of the results in terms of this artificial magnetic field. Okay, so maybe I would, yes, let me start with this Rashba-Dresselhaus spin orbit coupling and how we can what we observe in experiment and how we describe the system. So this is the again the experimental results of the reflectivity spectra in circular polarization basis. And then you observe that when we approach horizontal and mode to the vertical one can see that first of all there is the two parabolas they became shifted in k energy in k in momentum space, and also they became circularly polarized, and this kind of interaction in terms of spin orbit, this is exactly the interaction you find in solid state physics, and this is called Rashba-Dresselhaus spin orbit interaction. So there are two terms, Rashba and Dresselhaus, and if they are of equal strength, we can have exactly the solution which we observe in our system. So we expect and we observe the circular polarization splitting, and if one plot the whole dispersion in momentum in reciprocal space, one can measure, and this is these are the result of the tomography. This is the result of measurements. One can measure the paraboloid in polarization, the polarizing circular polarization, and of course the cross section of this paraboloid give the either 2 points or 2 circles which intersects or they touch each other, etc. So for this particular situation, when we have no additional splitting between the horizontal and vertical modes, and they are just in the resonance. One can now ask the question, but why circular polarization? Yes, we have horizontal vertical basis, and what is the region, the physical origin of this circular polarization? So this is the mathematical. I don't know if you can see it very smoothly, but this is the simulation of 2 modes. One is horizontal with n equal 2, so there are 2 antinodes, and one has 3, so there were 3 antinodes, and depending on the phase between them, but one can observe that the sum of them, the vector sum of them, is rotating on the one side and on the other side in circularly, and they rotating actually the same direction. So if that's okay, it's the direction from the point of view of the cavity, they circulate opposite direction, but from the point of view of light, which is is coming out from the cavity, they have the same circular polarization. So both they are sigma minus or both they are sigma plus. So this in this system, actually, if we just consider the finite k vector, not equal 0, but some finite k vector, we can even expect the transverse angular momentum on the surface of the cavity. Okay, so now the last paper which I would like to discuss. That's maybe not our last paper. The paper I'd like to discuss, it was published in November. So in that sense, this is our last paper. Indeed, this is the research going on this Rashba-Dresselhaus regime. So again, here, this is the plot of those parabolas. We have in y direction, we have those 2 parabolas split by this reciprocal momentum vector, and as you observed, we have this circular polarization splitting, inversion symmetry. It is present in our system, and we have no magnetic. I should mention this. This is although this situation is similar to Rashba-Dresselhaus term in solid-state physics. In solid-state physics, it is present only in the system when you have no inversion symmetry. Our cavity have inversion symmetry, and the origin that we observe it, this sigma plus sigma minus polarization splitting, even without magnetic field, is that the symmetry transformation between the electron spin, and the polarization of our light are different. So, for instance, you can consider the reflection of spin, a reflection of the polarization. But this was only the remark. Again, we are dealing with the cavity when we can observe now monochromatic light traversing the cavity, and at the regime which typically I will discuss now, the regime when we have those 2 rings of this paraboloid touching. We call also those paraboloids like valleys, yes, because they are circular polarized valleys in the sense that we have on 2-dimensional dichalcogenides. We have valleys, and indeed here we have also the states which are available for propagation of light in form of circular polarized valleys. In a system when there is a Rashba-Dresselhaus coupling of equal strength, it was shown in a group of, I suppose it was Princeton, Berkeley, and Stanford, that one should expect so-called persistent spin helix. What does it mean? It means that if the system, the evolution of the system is governed by the spin Rashba-Dresselhaus spin orbit coupling, then you can expect that the precession of spin is somehow symmetry protected. It means that the spin, the spin configuration depends on the distant travel in one direction, and doesn't depend on the distant travel in the other direction. And for electrons, one should expect the stripes of polarization in the form of the so-called spin helix. Depending on the exact Rashba-Dresselhaus term, it can be the spin helix which goes on the surface in, let's say, traverse or perpendicular to the surface of the sample. But this kind of spin coherence in the samples should be expected. And also this was important in at the beginning of the century. This paper of Bernevik was of the 2006, when the spintronics were looking for the spin transistor, and the people believe that with this persistent spin helix, one can protect the spin coherence in the system. Indeed, there were some measurements that the spin coherence times was increased by the order of or orders of magnitude. So if people observe this persistent spin helix, for instance, in Kerr rotation experiments, so they excite the sample and they sense, they detect the spin polarization in the samples, and so they observe how the spin diffused, and this diffusion was in the form of stripes. They can use magnetic field etc. And also we would like to observe the same phenomena in our system, but then we realized that this experiment which we are going to perform just resembles the well-known experiment of Young, which was done almost 200 years ago. So if we now just for a moment think about the interference pattern which was observed in the case of spin helix. So the interference patterns occurs, just iconic image of the interference pattern is double slit experiment. Yes, so in double slit experiment we have two slits of the distance at the given distance, and the light and the plane wave which passes through those two slits forms intensity fringes at the screen, and actually the slits, this experiment transforms the real space, so the distance between the slits, into momentum space, because those interference fringes, they appear at any distance of the screen, almost any distance, because it's too close, then it cannot be seen. But this is like a transformation between the real space and reciprocal space. And everybody knows that if one want to describe this interference pattern, then one has to take into account both slits. it cannot be explained just by the light passing through only one of them or some of those two slits. They must be both slits have to be taken into account. And typically the polarization is not an issue. So it means that everybody knows that the polarization should be the same in order to have the same the polarization between the two slits. Yes, they must be the same in order to have the maximal contrast of the interference fringes. I know that changing the polarization in between two slits is not very easy task, but the Young experiment or the beam splitters or Max Zehnder experiment and Michelson experiment, they can be described in very similar way. And in interferometers, using polarizing beam splitters or non-polarizing beam splitters give the similar results. So this problem is well known, and this is just a textbook problem, and one can consider the way the light make the interference, but also where can you ask the question, what happens with those interference fringes if we use polarized light? Yes, so for instance, we have this, let's imagine that we put two tiny polarizers, horizontal and vertical, into those slits, and we would like to observe the interference. And of course, one can say that there is no interference at all, yes, because the light passes and this cannot interfere destructively or constructively. But this is actually not the whole story, because nevertheless we can add the light and the phases of the light if there is a common coherence between those phases. So there is still the plane wave passing through the slits. And then, for instance, for horizontal and vertical light, one can observe that in a polarization space, there is a pattern of interference. So adding another polarizer in the front of the screen shows up the interference pattern again, and it chooses the proper polarization. Is this the same for the example here is just for, I don't remember from this textbook, 0 and 90-degree polarization. The same one can be for 45 and 135 degree of polarization. But interesting thing happens also when we have the circular polarization of both slits, and then we observe the pattern, which actually is called persistent spin helix, because this is what we should expect from this system. So in our case, we also can understand our experiment as a kind of Thomas Young experiment, double slit experiment, but now in reciprocal space. So using monochromatic light, we pass the light through two slits, but in reciprocal space. Yeah, these are the minima of the bands which are allowed for light to propagate through the cavity. And so we should observe also the polarization pattern, but not in intensity, because they have two orthogonal polarization, but in linear polarization, as it was previously suggested or shown, or is already known. So we would like to describe again our system in this term, but so it somehow resembles the quantum mechanical description. But of course, somebody can claim that those operators or those states are not well defined. But we have Maxwell equations, and we have we know how to propagate the light. We can pass the Gaussian beam of the linear polarization through the sample. We need to excite actually the valleys in momentum space. So we need to excite not only at k equals 0, but also at other momenta. So it requires the high numerical aperture and excitement in the form of the cone, so the divergent beam, and then one can calculate the beam which goes out the cavity, and indeed it is in this form which resembles, it's similar to what we can expect from quantum mechanics. So we have polarization of light, and let's say spatial term, and this spatial term is just calculated like an zero order Bessel function, and this zero Bessel function, the argument for the zero order Bessel function is very, very small. So we are dealing with this Bessel function of the order of 1, and we have the two sources of the beam. One is related to the one valley and the sigma plus polarization, and the second is the other valley, and also the relative phase is governed by the linear polarization and the incident beam. So with this, we can calculate all Stokes parameters as a real imaginary part, and the rest as free parameter. And then we can compare with experiment, and indeed we observe this kind of stripe. So we perform just a transmission measurement to the sample, and we observe the polarization stripe both in horizontal, vertical, or diagonal, anti-diagonal polarization on the detection. This is the confirmation from the model I present here, and another confirmation is provided by Helgi, and he calculated the propagation within the Hamiltonian, which with this planar propagation of light in Rashba-Dresselhaus regime. If we tune or we change the linear polarization, so we change the relative phase between sigma plus and sigma minus phases, we observe that the fringes indeed they shift, and they shift in such a way that this resembles sine and cosine between them. This system also might be interested from the point of view of other works. This is the just liquid crystal system when they use artificial spin of persistent. Okay, they did not call it persistent spin helix. They just use it this kind of polarizing plates in order to investigate random walk of electrons in the system. So this system is very similar to what we can observe in our system, but just by tuning the voltage and the orientation of the molecules. Okay, so but this is not the end of the story. As you have seen here, for linear polarization, we, let's say, excite those two valleys equally. Yes, so we have the equal occupation of sigma plus and sigma minus waves or photons in our cavity. So we, in general, we can introduce the parameters, we call it beta plus and beta minus, just to mark that this one is related to right and left-handed circular polarization. So this is just a replacement. Yes, for incident linear polarizations, they are equal, and there is a certain orientation, the phase between them. But how we can now discuss what happens if they are not equal. So we excite one of the valley with greater amount of the photons. or the light is propagating mostly in sigma plus or sigma minus. So this situation just is very similar to the situation that we are using only one slit in our system in Thomas Young experiment. Yes, if we use only one slit, then one can expect that we have no interference fringes, and we should observe only the intensity related to one of the slit. And in our system, we have the same situation. Sorry, this k should be equal 0 because we go straight forward to the screen. If we just normalize the incident beam, so the coefficient beta 1 and beta 2, beta plus and beta minuses are equal 0, then we can introduce another parameter, and it's Helix proposed to introduce this parameter in the form which is known from the discussion about the quantum and classical entanglements. Although I'm not going to use this classical entanglement in this presentation, because I know that there is a dispute in our society. What does it mean, the classical interpretation, if it is oxymoron or not, or what is the really real nature of the entanglement, that is non-locality and not inseparability, etc. But this, nevertheless, even about this discussion, we can introduce the parameter, which is very useful for the investigation, which is also can find it in recent review paper of Korolkova and with this parameter C defined as that, again we can calculate the stock vector, and then it occurs that the square of the S3 parameters and this new parameter C square is equal 1. It's yes, if you put this to the square and this to the square and add together the minus 2 beta plus beta minus changes into plus beta minus, and those term cancels. So in that sense, the S3 parameter, it is the way of measurement of the separability or non-separability. What's the meaning of this parameter C? Actually, this parameter C is defined in such a way that if the system is non-separable, so we have like linear polarization, or both valleys are excited equally, then we expect that there should be no S3 stock parameters, so there no degree of circular polarization, and then we expect the presence of the interference fringes, while in the system when we have no coherence between two valleys, yes, so there is no common phase between them, and then we have the source of sigma plus and sigma minus polarization, then the degree of circular polarization is maximum, and we should not observe the interference patterns. And we performed this similar experiment with the halogen lamp in the space tomography, and we observe the S3 parameter. This is not S3 parameter. This is the 3 parameters. We observe indeed this is non-zero except the central part where there is a light, but the S3 parameter is equal to 0, and the light coming from this is non-separable in terms of the degree of freedom of the position and the polarization. This splitting between sigma plus and sigma minus also resembles another experiment in quantum mechanics. It's called Stern-Gerlach experiment, when Stern and Gerlach passes silver atoms and they discover the splitting of spin up and spin down spins, and similarly we have a model of the Stern-Gerlach experiment here. Okay, then this paper was chosen by physical reviewers by as an editor suggestion, and it was published 1st of November. The first author of this paper was the Mateusz Król, and also is the author of all those beautiful graphics. And Mateusz is finishing his PhD and next year, so if you have interesting propositions for Mateusz, do not hesitate to contact him. Now I have a few minutes to introduce the lasing. Lasing was done by Marcin Muszyński, another PhD student. We managed to dissolve the pyrometan, the P580 laser dye inside the liquid crystal in this microcavity. It was done by also by Military University of Technology. We excite the cavity with Q-switch nanosecond laser, green laser, and depending on the intensity of the power of the excitation, we observe either the luminescence from the cavity mode, but then at certain threshold, the horizontal mode has the increase of the intensity, and the lasing occurs at the bottom of this parabola. And we observe that the line with over the threshold is decreases, and the energy actually this also changes, but it's not a blue shifted, it's red shifted, and there are there might be many reasons that we observe such kind of energy shift in our system. But what is important that this lasing occurs in horizontal mode. When the horizontal mode, we can tune easily with our voltage. So here there was the emission and the comparison in logarithmic scale between the reflectivity. Maybe I can play it again. And the reflectivity and the emission in logarithmic scale, and you observe that indeed the lasing occurs in the horizontal mode, and it follows the rotation of the molecules. We had the tunability range of about 40 nanometers, and this experiment can be repeated many times, in many series, but it is pulse experiment, yes. But interesting thing occurs when we tune our system to Rashba-Dresselhaus mode, and then we observe this sigma plus sigma minus lasing. Yes, because now we have a laser action which takes place from this bottom of two orthogonal polarized valleys, and it is observed in energy momentum coordinates, are also in reciprocal space of the two spots, but also we can observe it in real space, and so we expect that from those two spots, so we should observe the persistent spin helix in our system. And now the argument for this function at the bottom of the parabola, this energy is equal minus this term, so this is just equal 0. So stock parameters are very, very simple in this case, and this is what we observe. We observe indeed the stripes yes, in horizontal, vertical, diagonal, anti-diagonal, this is the histogram of the stripes. You see that one stripe has maximum, the other has a minimum, but they are shifted in phase as we expected. We observe also that the beam is diverged, but nevertheless, so we have sigma plus and sigma minus. Finally, on the one side, we have the emission from circular polarization right-handed and for another left-handed. So there must be some three stock parameters, non-zero stock parameters. But I would like to show that the spot, the excitation spot was relatively small, like 5 microns, and the rest of the polarization of the system was somehow protected by the Hamiltonian and the equation of motion. So we managed to do that. Okay, I have to finish, so maybe I will mention only the plans for the future. We are limited in our research to room temperature, because on the room temperature we can have the rotation of molecules, but there are a lot of system which can be integrated, potentially can be integrated in, and giving to, let's say, the hope for strong coupling with organics, and the strong coupling was already presented. So we hope that we can also take part in this research. There was a beautiful seminar of Team Gao, and they show already the very similar system of liquid crystals and perovskites. So there is the way to put another emitter also to the system. We experiment with, for instance, the transition method dichalcogenides, which were also embedded inside the cavity. And we had some tunability, unfortunately, without the strong coupling. There is another research, very interesting research, ongoing research on birefringents in general, and topological or Berry phases in birefringent materials. So we would like also to take part of it. There is another group which shows the polariton lasing and helical polariton lasing from the valleys. This is very recent archive I found in the actually this evening. But also they show the very similar optical activity induced lasing. So this is our results, the conclusions. So we were able to fill the the cavity with clister, and now we try to use this system to do some interesting, I hope, interesting physics. We would like to use this spin orbit interaction, synthetic magnetic field, etc., to develop new devices to enter the field of topology. I showed you already the device like a tunable laser. Let me acknowledge again the whole group who work on this field. I would like also acknowledge the Horizon 2020 FET Open action, which we started in September among IBM, CNRS, Southampton, and the Military University of Technology. And thank you for your attention. That's all.
Thank you, Jacek. Yeah, that was much better. I wonder what you see through that. So, okay, thank you for this very nice presentation. So let's start with questions. I am aware that you have to go for a lecture very soon, so I will try to keep it sort and manage the questions. So if you have a question, please raise your hand. And let me see. Okay, so Tamsin Cookson from school.
Hello.
Thank you for the nice talk. I was wondering about this inseparable and separable states that you showed. You showed them coupled, and then you showed being able to turn one completely off by tuning the excitation laser. Can you do that in steps and have one of them at full and one of them at 50%? Or is it the same intensity and or just one off kind of thing? Sorry, I don't know if I phrased that well.
As I understood your question, you are asking if I can change between this occupation of this sigma plus and sigma minus. This was your question?
Yes.
How to change? Yes, of course. There's sorry, I'm looking for better question. It's over there. So just by choosing let's say the amount of the polarization of sigma plus and sigma minus in incident light, so the incident polarization, one can choose between sigma plus, sigma minus on linear polarization and or elliptical. Yes, so this is, we have the whole blocks here, and by this you can tune not only the visibility of the polarization fringes but also the amount of non-separability and non-separability of the states in a sense of S3 parameters, which is typically in that case we can interpret S3 as the separable state. Separable because if you have the fringes, and the fringes are only occurs at the surface of the cavity. I didn't mention it. I forgot this. The normal Young experiment transfer the distance, the real space, into the direction, into reciprocal space. In our case, we have these two slits in reciprocal space, and this transfers into the spin pattern, but this is only it exists on the surface of the sample. But because anyway, far from in a far field, we observe that the sigma plus polarization is emitted from the sample, and this momentum and the sigma minus an opposite momentum. So for the far field, both states are separable. Yes, because now the position and the polarization is completely separable. By knowing the position, I know the polarization. While on the surface of the sample, when I have this those two states, and they have linear polarization, in order to have this interference pattern, I have to use both. Yes, so in that sense, those two states are necessary to have the interference pattern. So in that sense, they are inseparable. But by just changing the polarization of incident light, I can excite differently those two valleys and have the different pattern, because I shift with linear polarization and shift the position of the maximum, let's say, of the fringes, and also the amount of the sigma plus or sigma minus light emitted through the sample. I hope I answer your question.
Yeah, I think that I was asking if it was completely tunable and you had complete control over this interaction and the degree of separability. So I think
the only thing I couldn't do is, for instance, I couldn't excite both valleys sigma plus or both valleys sigma minus. Yes, or inverse the sigma plus and sigma minus. This is so in the terms of Bell states, I do not have access to all the Bell states.
Okay. Thank you very much.
Okay, thank you, Tamsin. Anton Zasedatelev from Vienna.
Oh, thanks for a very interesting talk. I have a very quick question. You mentioned on slide number 39, I guess, that for solid-state systems, by rotating the spin, you can somehow protect the coherence of the spin system, right? I was wondering what the mechanism behind. Could you elaborate this a bit?
39 or 49?
Oh, no, it was a bit earlier. On your slide.
No, but this is not the.
Basically, the question: how by the rotating the spin in your system you can make the coherence more stable in the system? What's the mechanism?
I suppose I mentioned it over there. So
yeah,
I said at the end that the spot was very tiny, but nevertheless, when the light is propagating inside the sample, because this is the cavity, there are multiple reflection, and of course S1, S3, and S2 stock parameters, they are normalized. So even if in normal let's say space, you just see one big spot. There are some light diffuse, and normalize it. You increase this light, and this is the same kind of protection that's like it was introduced by Bragg for spins in solid state physics. So the evolution of spin or the precession of spin now is governed by spin orbit interaction, is governed by Rashba-Dresselhaus spin orbit interaction. So they have no choice. They have to, if they want to propagate inside the quantum well for electrons or microcavity in spin, they have to form this stripes, and this stripes pattern is robust or quite robust.
Okay. Well, I mean, I guess my question was more about the helix patterns. The helix.
The helix.
Yeah. You mentioned there that the helix states somehow they preserve the coherence in the system.
No, I don't remember. I said that this is the proof of the coherence of the system, because we have two laser beams, yes, and they have the same oscillator, yes. So they have the same phase at the origin, and the molecules they have the same origin. So because without if they are very independent lasers, yes, we won't observe the persistence spin helix or the polarization coherence. Yes, so we would rather observe on the sigma plus sigma minus. This kind of pattern, and this kind of pattern comes just for the, let's say, incoherent light, and this is for coherent phase coherent light.
Okay, maybe we can discuss.
Incoherent is not a good word here, but
yeah, I mean, it's tough question. I guess we can discuss it probably later, and probably anybody else has a question.
Okay. I'm sorry if I didn't answer your question.
That's fine. I think Jacek, you meant that it is there is a relation between the different polarizations. It is not that necessarily the light is coherent. Yeah.
Maybe yes.
Yeah, but on the same topic, if we start from the nomenclature, persistent spin helix, how do you think one could check could test how persistent it is? This means that it's persistent against some external perturbations or some noise in the system. And so far, we are observing it, but nothing has been done to really test how persistent it is against some external influence, let's say, either dynamic or of any other type. So
this is a good plan for future research. It is okay. In solid state physics, people put this persistent helix, for instance, in magnetic fields. Yes, so they change magnetic field and they observe how the diffusion of electron changes in due to the presence of Lorentz force. And I believe that this, as far as we can consider the propagation of electrons or propagation of photons as ballistic without scattering, probably this evolution is indeed governed by the Rashba-Dresselhaus spin-orbit coupling. But then, in case of scattering, we can see it should be somehow protected, because this was the hope for spin transistors. Yes, so within this persistent spin helix, you have a long distance precession of spin, but you can somehow control this precession. You know what is the magnetization of the spins at the origin and the source of the drain. And maybe it's a similar situation we can have with polarization, but you know, when I look in the persistent spin helix for the electrons, now I recognize that indeed for electrons they also did exactly the same double slit experiment in reciprocal space. So that means that it's somehow this spin of electrons is kind of polarization of electrons, but maybe I'm going too far with the interpretation. But we can use our interpretation also to understand what is the meaning of the persistent spin helix. I know that it comes from the equation, and I like that something is explained by the theory, yes? But I suppose that if we just introduce that, okay, with this Rashba-Dresselhaus, there are two valleys, there are the sources of electrons, they interfere, and you should observe this interference pattern. It's elegant, so I like it.
I have a follow-up from this one, coming to the work where you recently doped the cavity with dye molecules, so you introduced optical gain and you show lasing. And then you mentioned also the work in using perovskites inside the liquid crystal microcavity, where lasing was also observed. And a couple of weeks ago, we had a talk from Tingye Gao. Yes, exactly. So what would be the advantage of having this kind of lasing in the strong coupling regime? So optical gain introduced, observed with perovskites, maybe not in the strong coupling. There was a huge debate last time, but also in the weak coupling regime in the work that you have done. So what would be the advantage here of bringing the system in the strong coupling regime? Why bother?
Except that the person who does it will be the first one. In a strong coupling regime, we believe that we are dealing with Bose-Einstein condensates somehow, and this lasing is due to this macroscopic properties of Bose-Einstein condensates. So having this spin orbit interaction and having this artificial magnetic field allows you to modify the Bose-Einstein condensate, and this is not a trivial task in atomic physics and even in semiconductor structures. So I suppose that it opens the possibilities also for the additional research. And imagine about the persistent spin helix or magnetization or Bose-Einstein condensate in your system. Yes, so you have a spatial modulation of polarization of Bose-Einstein condensates. So this is yes, that might be another topic for the research if somebody showed this in the future. And there are several systems which we have to test, and I'm very glad that other groups they join our research. Yes, we are not alone, and we can share our experience and work on this topic.
Thank you. We have last two questions. One is from Tamsin Cookson, again, Caltech. So Tamsin, please.
Yep, I was wondering on the, when you're in the, I can't pronounce it, the Rashba-Dresselhaus regime. Sorry, I can't pronounce that at all. If you excite with a lattice or two spots instead of a singular Gaussian, what do you expect to see in terms of interference within these two K-rings?
This is also a very good question. Yes, how to get I missed the word. How to use the spin-orbit interaction and spin-orbit coupling in a case when you have the patterned samples or the samples when you excite as you do in Caltech with multiple beams. I suppose that this is the next idea for the common research, yes, among Caltech and our team. So what of course what you expect, this is the dispersion relation of the free particle. Yes, so in solid state physics, the Rashba-Dresselhaus occurs in Brillouin zone. So this is a periodic structure. But here we do not have periodic structure. We have Rashba-Dresselhaus splitting, and this is the free particle. If you add the periodic structure to this system, you should expect that you will also have Brillouin zone, two-dimensional Brillouin zone, but spin orbit coupled, spin orbit split. And this is a good research which I would like to also do with this Topolite project about the different structures or periodic structures on together with artificial synthetic magnetic fields, synthetic gauges, and spin orbit coupling. Yes. So yes, this is it opens new possibilities. Oh, short question answer.
Thank you.
It's a very good plan.
Thank you, Jacek and Tamsin for the question. A last question from Anton Zasdadlev.
My question is the strong coupling with these dipole cavities. How small could be the cavity? Because I guess to observe this beautiful physics, spin physics, you need to have some numbers of antinodes in your cavity. How small the cavity should be such that you afford this spin stuff and see the strong coupling? Yeah?
Okay, yes, there is a balance between the Rashba-Dresselhaus regime when you need to use multi-mode cavity because you need the subsequent modes and not too far to each other to cross. But also you should have not too many modes because otherwise you lose this strong coupling. So I cannot give you right now the answer. We are trying. Yes, the typical thickness of our samples is of the order of between 2 and 5 microns, but 5 microns is very thick. Yes, so
yeah, it's very challenging to get lazy other
exactly,
stuff
yes.
with such a huge
very good question, but we don't know yet.
Okay, thanks.
You have to have the space for molecules to rotate, yeah? And the molecules which are close to the surface of the mirrors, they do not rotate. So there is also some molecular layer which does not respond to electric field, and also you have to take into account.
Sure. Okay, thanks a lot for the very interesting talk. Nice.
Thank you very much.
So Jacek, thank you very much for coming today and really answering all these questions and the very nice presentation, and everyone who joined us today for this talk. There will be an announcement for the next one, which will be in a couple of weeks' time. And until then, good to see you all and have a very good day.
Thank you very much.
Bye.
Bye.
Thank you.
Bye.
Bye. Thank you for the invitation. Thank you very much. Bye.